Good morning friends. We have already seen methods to analyze a given system with the help of classical control theory. When we talk about classical control theory, we'll have two domains. Number one is time domain and number two is frequency domain. When we talk about method of analysis with the help of time domain, we include the methods of root locus. While on the other hand, when we talk about frequency domain methods, it includes board plot, polar plot, Nicholas chart and Nyquist plots also. Though in some literature, Nyquist plots and Routh array criteria are listed among the stability criteria, but we know that basically polar plot is a approximation of Nyquist plot. So we will also include Nyquist plot is a frequency domain method to analyze a given system. Well, so when we talk about the limitations or advantages, there is a trade-off between time domain methods and frequency domain methods. Let us first talk about the time domain methods. When we talk about time domain method, this method is relatively tangible. It is a direct method. Whatever you do, you are able to visualize those things directly. While the main thing is that it requires a transfer function. Beforehand, you analyze a given system with the help of time domain method. On the other hand, when it comes to frequency domain method, it doesn't require you to have a transfer function. If you are having a transfer function of the system, it is well and good. If you are not having a transfer function, you can directly correlate the input-output relationship. You can directly capture the input-output relationship and then you can analyze the given system with the help of frequency domain method. So the stringent requirement of having a transfer function is one of the limitation of time domain analysis, right? While on the other hand, we are not required any transfer function in case of frequency domain analysis. Well, but the main limitation of frequency domain analysis is that when you will go to the higher semesters or when you will read the theory of higher control system, will come to know that the method of frequency domain analysis are basically not applicable for non-linear systems. These methods are only applicable for linear systems. Okay. Now, having clear about the methods of analysis, let us talk a little bit about design. So we are having a open loop system. We deploy a feedback to that particular open loop system. We'll have a controller so that we can minimize error, right? This is the basic configuration of any control system according to the classical control theory, right? But before that, when we talk about just a system without any feedback, we are not having anything, just a single block. Block is what? There may be any transfer function sitting inside that particular block. It may be a mechanical system, it may be electrical, chemical or anything else. So it's a simple system. It might have some limitations in terms of stability. For example, suppose a system is there to measure temperature. Take a very simple example. Let us talk about thermistor. Thermistor is basically, in language of control system, it is just a system, right? Though it is a sensor, but we can say it is a system. So it is having some certain limitation of range, right? It can measure a value from say minus 20 degree to somewhere around 120 degree, plus 120 degree. Beyond that, it will not be able to measure. So similarly, we are having some stringent stability criteria. If system go beyond that particular criteria or come below that particular criteria, it will not work properly. So in ideal world, it seems like, okay, we are having a system and we are having some constraints applied on that system, maybe a stability constant, maybe some operational constants, maybe some value of zeta and all those things why you have read all those parameters in while discussing the specification of time domain analysis. So we are having various specification, and you are having a system which satisfies all those specifications, right? Ideally it seems sound, but what happens when you come to real worlds? A system may deviate from its boundary. When a system deviates from its boundary, you need something, some mechanism to compensate for it. So when we talk about compensator, you directly recall a word controller. So you may have confusion that okay, controller is also doing something, it is also minimizing error, and now you are talking about compensators. So let me clear you the thing. When you are having an open loop system, and you want that open loop system to be confined by a certain range, then you will use compensator. So compensators are basically used for open loop system. While when that open loop system, though with the help of that compensator, comes under the operational range, then only you will be able to deploy that open loop system into a feedback system. And after deploying that open loop system into the feedback system, you talk about the error. If you are not satisfied with that error, you want that error to be minimized, because you want that your output should be as close as possible to the input signal. So you deploy another device and you say that it is controller. It may be PID, PI, or other various kinds of controllers are there, but we mostly in our this particular course we mostly talk about this PI, PID controller or PD controller, something like that. So the aim of this controller is to minimize the error in the closed loop configuration, while the aim of compensator is to compensate for something. Go to the word literal meaning of this compensator. Compensator means what? Something happened negative to your system, something bad has happened to your system, and now you want to mitigate that particular thing, means compensate for that particular thing. Then you use compensator, and then you will have your whole package of open loop system under a certain operational range. When it is under a certain operational range, when it is stable, or when it satisfies some parameter, then only you can deploy this open loop system into a feedback control system. And then depending upon that, whether you are satisfied with that particular error or not, you apply various kinds of controller. So now it is clear what is difference between controller and compensator. You can say roughly, you can say that compensator may be some kind of controller, but no, we are having a different terminology in literature. So for open loop system, when we will try to compensate for some parameter, maybe zeta, maybe a stability range, whatever it may be, we will name that device, that circuit, as a compensator. And when we will talk about closed loop system, and we are more concerned about the error of the system, to minimizing the error, then the device you deploy, you will say that this is a controller for the system. So now let us start the theory of compensators. The performance of a feedback control system is of prime importance. A well-designed control system should have the following properties. It should be stable. The controlled output should follow the changes in the reference input without undue oscillation or overshoot. That is, it should have suitable damping. It should be less sensitive to the system parameter changes. We know that due to wear and tear, the parameters of the system changes due course of time. If a particular system consists of some electrical parameters, it may be resistance or inductor or capacitor. Due to wear and tear or due to some environmental effect like temperature, the system parameter may change. So the desired ideal system should be less sensitive to the parameter changes. It should be able to reduce the effect of undesirable disturbances. it should have as little error as possible. So these are certain desirable requirements for the ideal system. But a feedback control system that provides an optimal performance without any necessary adjustment is basically very rare in nature. And usually it is necessary to compromise among these many conflicting and demanding specifications. In general, there are two situations in which compensation is required. In the first situation, the system is absolutely unstable and the compensation is required to stabilize it and to achieve a specified performance. While in the second situation, the system may be stable, but the compensation is required to obtain the desired performance. Although many different types of compensators can be used, the most commonly compensating electrical networks are: one is lead network, or it is also known as lead compensator. I will come to know why these are called lead network or lead compensator. Second one is lag network or lag compensator. And third one is lead lag network or lead lag compensators. These basically it is either lead network or lag network is basically decided by the sinusoidal input signal. If a sinusoidal input is applied to a network, a sinusoidal output is obtained, and if the steady state output leads the input, the network is called lead network. And if the steady state output lags behind the input, the network is called lag network. That is why the name lag. And this is basically phase lead and phase lag. While in case of lead lag network, both phase lag and lead occurs in the various different frequency regions. The phase lag occurs in the low frequency region and the phase lead occurs in the high frequency region in case of lead lag network. That is why they are known as lead lag network. So we are having various configuration for in which these networks can be arranged. So number one is series or cascade compensation. Second one is parallel or feedback compensation. Third one is series parallel compensation. So coming to first, series or cascade compensation. If a compensator, see here it is a compensator. See GC, if GC is written, it means C for compensator. If nothing, if C is not there, it means just a forward path transfer function, and HS is, you know, that it is a feedback path transfer function. So if the compensator is placed in the forward path, here it is placed in the forward path because this path is basically forward path. The scheme is known as series compensation or cascade compensation, right? Accordingly, we can have parallel or feedback compensation. See here, it is basically not a compensator. These are basically, we have splitted the transfer function of plant into two parts, G1s and G2s, and the compensator is here, right? So if the compensator is placed in minor feedback, see here it is a minor feedback, a smaller feedback is there and the larger feedback is this one. Okay, so if the compensator is placed in the minor feedback path, the scheme is known as parallel compensation or feedback compensation. And we can have also both these scheme combined into a single diagram. So here it is GC1, so here it is one of the compensator, here it is second compensator. So one of the compensator is in series connection and another one is in minor feedback connection. That's why it is known as series parallel compensation. Okay, so now coming to the selection of compensator, on which basis you will be able to select a particular compensator. Basically, the selection of compensator scheme depends upon the specifications.
the power level at the various signal nodes in the system, available component, economic consideration, and also based on some designer's experience. So there are so many criteria on which you can select a particular compensator. When we talk about the design approaches, means how to design a particular compensator for a given specification, we are having two different methods. Number one is root locus based method, and number two is board diagram based method. Basically, we all know that the performance of a control system can be described in terms of time domain as well as in frequency domain parameter. The time domain parameter, if you can recall, are basically something like peak time, maximum overshoot, settling time, maximum allowable steady state error, or something like that. Okay, so if the performance measure is given in terms of time domain parameters, then the method of root locus is applied to design that particular compensator. Okay, similarly, the performance measure of a feedback control system is also described in terms of frequency domain parameters. We have also, in one of the lecture, we have correlated time domain parameter to that of frequency domain parameter, right? So some common frequency domain parameters can be like resonance peak of the frequency response, resonant frequency, the bandwidth, the phase margin, the gain margin. All these parameters are basically frequency domain parameters. So if the specifications are given, specification means what? You are required to have a given, you are required to achieve a given phase margin or a given gain margin or a given bandwidth or a given resonant frequency or a given a resonant peak. uh, then in that particular case, this you apply the method based on the board diagram, right? So in the classes to come, we will first read in detail about the compensators. Means in the next class we will talk about phase lead compensator, then we'll talk about phase lag compensator, then phase lead and lag compensator, and then how to design compensators using this root locus method when the specifications are given in the time domain, and how to design the compensator using board diagram method when the specifications are given in frequency domain. So we'll stop here for today. Thank you for listening.